from the previous slide, you already see that sample of the element can contain several isotopes, right? So the next thing we're going to take a look at is we are going to take a look at how each of those isotopes contribute to the average atomic mass. Okay, so we are going to use this equation right here to help us to find out the average atomic mass. Okay, so this sigma right here represents summation. Okay, so what you are going to do is that you are going to add all the available isotope mass multiplied by its fractional isotope abundance. Okay, so after you add them all together, that is going to be the weight average of the atomic mass. Okay. All right, so let's take a look at example. Okay, so for example, we are going to calculate the average atomic mass in atomic mass unit for carbon. Okay, so this, what you see here, each of these would be represent isotope of carbon-12, carbon-13, carbon-14, right? Because each of these isotopes contain different number of neutrons, but they have the same number of protons. So therefore, in this case, you probably notice that the isotope mass, they are going to be different. Okay, so the reason for that is because they have different number of neutrons that contribute to the mass, right, for the isotope. Okay, so show here is going to be the list of percent abundance. Okay, so for example, in nature, if you have 100% of carbon sample, right, you are going to end up with 98.93% of carbon-12 and 1.07% of carbon-13, and the trace amount would be for the carbon-14, for example. And because the equation for atomic mass involved with the fractional isotope abundance, so therefore in this case we would need to be able to convert from percent abundance to fractional abundance first. Okay, so just note that whenever that we talk about percent, just know that percent is out of 100. Okay, so for example, if I say that there are 75% of female students, that is going to imply that the rest of it, right, which is 25%, is going to be for male students, right? So it's out of 100. Okay, so that means in this case, if you add all the percent together, right, so all of these need to add up and equal to 100. That's what it means. Okay, so for the fractional abundance, this is going to, the fraction would be out of 1. Okay, so that means in this case, all of these add together need to equal to 1, right? So that means in this case, this side, which is the fractional, is going to be 100 times less than this side, right? Because you are going to make sure you are going to go from 100 out of 100 to out of 1, right? So that means what we can do is that we are going to divide all of these percent abundance by 100 in order to get the fractional form. Okay, so what we're gonna get would be 0.9893, right, for the fractional abundance for carbon-12, and 0.0107 for carbon-13, and then the trace amount of carbon-14. So I'm just gonna leave it as dash because it did not give us any number. Okay, so again, because fractional is going to be out of 1, so therefore if you add all of these together, it's going to come out to be around 1, right, because we did not count the trace amount. So now we are going to use this equation to help us determine the average atomic mass for the element. Okay, so in this case, I'm going to leave it as equal. It said equal the summation of isotope mass multiplied by fractional isotope abundance. So I'm going to look up the isotope mass. For carbon-12, the isotope mass of carbon-12 would be this, right? So it would be 12.000. I'm going to list out everything, because those are going to count toward number of sig-fig, right? So all of those are going to be significant because it's a 0 after the non-zero digit. Multiply this by fractional isotope abundance, okay, so which is 0.9893. Okay, now we are going to include another isotope, right? Because this summation tells us that you're going to add that to another isotope. So I'm going to add this to another isotope, which is the isotope 13. The mass of isotope 13. This mass number just tells you only the number of proton and neutron, not the mass. Okay, so this is the mass right here. Okay, so when you take the mass of proton and neutron and add them up, so that would be the mass. Okay, so this one is going to come out to be the mass of carbon-13 that is given multiplied by its fractional isotope, which is 0.0107. Okay, so since we don't know what is the fractional abundance of carbon-14 in this case, you can just ignore it. But if it gives you a certain number here, then you need to include that as well. So you're gonna add to the mass of carbon-14, right? And then add to and then multiply by its fractional abundance. So right now we don't know, so I'm just gonna leave that. Okay. So what you are going to do next is you are going to follow the order of operation. Okay, so I'm going to multiply these two numbers Okay, so that is going to give me 11.8716. Gonna add this to the product of this operation. Okay, so that is going to be 0.1391359. Okay, so then you are going to add them together. If you add them together, that is going to give us 12.01074. What is the unit of this? Well, since the mass of an atom, the unit of this is going to be atomic mass unit. It's going to be in atomic mass unit. Sometimes some textbook we just use U is describe the same thing. Okay, so AMU or U is the same thing. It's atomic mass unit. Okay, so it's the mass of one atom. That's what it means. Okay, so the average mass of carbon atom in this case, right? That you average all the isotope together. So now let's take a look at this. Okay, so the next thing we need to take a look at is going to be the sigfig, because this comes from the measurement, right? We measure the mass of each isotope. So that means it's going to have some uncertainty that come with it. So I'm going to go by the order of operation. Okay, so the first one that we did is this one. Okay, so this one is follow multiplication. So therefore we need to count number of sigfig. So this one contains 8 sigfig. Okay, so this number right here contains 4 sigfig. So therefore, the product of this multiplication is going to need to contain 4 sigfig. Okay, so I'm going to underline it. Remember, I don't round it yet because we are doing rounding at the end, right? So for the final answer only. So therefore, in this case, we are going to have 4 sigfig. Okay. Do the same thing for the second operation, right? So this one right here, I'm going to count that. So this one also have 8 sigfig. This one contains only 3 sigfig. Okay, because we count 1, 2, 3 there, the leading 0 are insignificant. Okay, so total would be 3, right? That's going to limit your final answer. That would be 3. So I'm going to underline 3 sigfig. Now, the last operation that we did is addition. Addition don't follow the least number of sigfig, but it's follow the least number of decimal place, right? So that means in this case, we need to count the number of decimal place. So if this if the answer from the first operation here, 4 sigfig, right, according to this, is going to contain 2 decimal places. So I'm just going to do 2. Okay. Same thing for the second operation. This value right here contains 3 sigfig, right, from the digit that we underline, right, from the previous operation. But this digit contain 3 decimal place. So I'm just going to do 3. Okay, so remember the last operation is addition, so we're going to go by the least number of decimal place. So the least number of decimal places is going to be only 2 decimal places here. Okay, so therefore your final answer going to be limited by the number of decimal place, which is only 2. So we're going to cut right here. Okay, so 2 decimal places. So in this case, 0 at the end. So this 0 right here make us to round down, right? So that means the final answer would be 12.01 AMU. So that would be the correct answer with the correct sigfig and unit as well. Okay, so you can write right here, right? So the answer would be 12.01 AMU. Note that if you're looking at this, as I mentioned before, right, because this average mass right here is the weight average, right? So the one that has the most abundant, right, they are going to contribute the most to the average mass, right? So in this case, you probably notice that the average mass here come out to be similar to what we have for the weight of the carbon-12, right? It's come close to that. So to tie back with the periodic table, just note that the number that contains the decimal point right here, that is going to represent the average atomic mass. Okay, so for example, carbon would be 12.01. Okay, so come from our calculation as well, right? And for oxygen and potassium, it would be this number right here that written. So those are going to represent average atomic mass. Okay, so that you actually do the weight average of mass of each isotope. All right, I would like you to pause the video now and complete this exercise 3. Okay, so when you finish, then let's check your work together with me. Now let's check your work together with me. Okay, so pretty much this is what I have here. So you are going to multiply isotope mass of magnesium 24 together with its fractional abundance and do the same thing for magnesium 25 as well. And the last one is for magnesium 26. Okay, so if you do all of these operations, so this is what I got for each of those. Okay, so if you add all this together, this is what I get here. So the last step would be sigfig, right? So I'm going to walk you through sigfig again. Okay, so sigfig, so this contains 4 sigfig. Again, the reason why I count sigfig because this is multiplication. Okay, so this is also 4 sigfig. So therefore, the following number would be limited by 4. Okay, so, but remember, I don't round, I just underline. Okay, so this should be 4 sig fig. If I count the number of decimal place, this 4 sig fig would contain 2 decimal places. Okay, so the next one, right? So this one contains 4 sig fig. This is also 4 sig fig. So therefore, this one would be limited by 4 sig fig. 4 sig fig, but the decimal place would be 3 decimal places, right? Because 0.531, that is 3 decimal places. Next one, right? So this is 4 sig fig. This one 4 sig fig. So therefore, this number going to be limited by 4 sig fig as well. This 4 sig fig contain 3 decimal places. So addition, right? So the last operation is addition. So that it's going to go by the fewest number of decimal place. So the fewest number of decimal place would be this one right here, 2 decimal places. So therefore, your final answer would contain only 2 decimal places. So you're going to cut right there. Okay, so 5, you're just going to round up. Okay, so it would be 24.31 AMU. Okay, so that would be your final answer. Again, to check your answer, okay, so this number right here, which is the average, the weight, average atomic mass, right, it have to come out close to the one that contain most or contribute most in nature, right? So if you're looking at this, right, so magnesium 24 contains 78%, right, almost 79%. So therefore, in this case, makes sense, right, that your average atomic mass come out to be closer to the mass of magnesium 24. Okay. Now, before we move on to the next example, I would like to point out something. Okay, so let's say that if this problem doesn't give you any percent of, let's say like magnesium 26, let's say that this number right here were not given to us, right? So we don't know about how much is available in nature. So how would we know, right? So what would be the number that we need to multiply here? Remember what we see here, right? In terms of abundance, right? So it's reported in percent. So again, what does percent mean? What percent mean is how to be out of 100. So that means all the percent abundant of magnesium 24, right, together with magnesium 25 and magnesium 26, all of these need to add up to be 100%, right? Because percent mean out of 100. So therefore, in this case, if you are not given the percent of magnesium 26, you should be able to find out that percent because you know the other two, right? You know the percentage of magnesium 24 and you know the percentage of magnesium 25. So therefore, in order to find out the percent of magnesium 26, what you have to do is add these two together, right? So add these two together and then subtract from 100 because all three of them need to add up equal to 100%. Okay, so just make sure that you understand that. Okay, so if the percent abundance is not given to you, right, but it's giving you other percent abundance, you should be able to deduce to get the not given percent by knowing that the percent is out of 100. Okay, and the type of problem that you are going to encounter would be when the problem gives you the average atomic mass and it asks you to find out the percent composition of each of the isotopes. So I'm going to use the same equation to solve this type of problem. Okay, so we are given the average atomic mass. I'm going to start with the average mass of copper, right, which is 63.546 that is given. I'm going to omit the unit for now, okay, to avoid confusion. And I'm going to set this up equal to the isotope mass multiplied by its fractional isotope, right, and add on to the next one, right, that we learned earlier. Okay, so in this case, the isotope mass of copper 63 would be 62.9296. I'm going to multiply this by its fractional abundance. Okay, so let's say that this fractional abundance of copper 63 would be X. Okay, so this is equal to fractional abundance. Okay, so if you want to know percent, you can convert that by multiply this X by 100, right? So I'm just going to use this as fractional abundance for now. Remember, fraction or fractional is out of 1, right? So everything need to add up equal to 1. So therefore, since we have only 2 isotopes, right, we have copper 63 and copper 65 available in nature. Therefore, the fractional abundance of copper 65 is going to be 1 minus X, right? Because together these two, when you add this X and this 1 minus X together, it need to equal to 1. But because out of 1 fraction is out of 1, Okay, so similar to percent, right? So your product of percent of these two, when you add them together, right, the percent abundance need to come up equal to 100, right? So if you want to check your answer, that's how you do it, right? So the percentage of copper 63 and copper 65, when you add together in terms of percent, it need to come out to equal to 100. If it doesn't equal to 100, that means your calculation or your setup for the calculation is incorrect. Okay, so that means for the next isotope, copper 65, I'm going to do 64.9278 multiplied by its fractional isotope, which is 1 minus x. Okay, so again, because fractional isotope of copper 63 add to the fractional isotope of copper 65 need to equal to 1, right? So that's why we need to set it up this way. I don't set up as y or z or other variable because I cannot solve two unknown variable. Okay, so the reason why I have to make to be one unknown variable because it's allow me to be able to solve for this x. Okay. Next step would be I'm going to pretty much rewrite everything again. So 63.546 here equal to this would be 62.9296x. Add, I'm going to distribute this number into the parentheses, right? Because we need to do this operation right here. So multiply them inside. You're going to distribute that. So what you're going to get 64.9278, right? Because you multiply by 1, and then minus 64.9278x, right? Because you multiply to x. The next thing is you are going to combine. So these two contain x. So therefore you can combine these two. Okay. So if you combine these two, you are going to get negative 1.9982x to 64.9278. Right, so this size still the same, 63.546. Okay, so the next thing is, well, this number right here doesn't contain any unknown variable, but this one also doesn't have any unknown variable. So I'm going to move this number to the other side, so that way the unknown variable would be by itself, right? So I'm going to, so this is addition. So I'm going to subtract this number on both sides. So minus 64.9278 minus 64.9278. Okay, so it will come out to be negative 1.3818. So equal to negative 1.9982x. Now to get rid of this part, right? So that way we solve for x, you are going to divide both sides by this value right here, negative 1.9982. Negative 1.9982. And then x would equal to 0.6915. Okay, so this 0.6915 come out to be a positive value. Makes sense, right? Because we looking at how much is available, it should be a positive value, right? So if you get a negative, that means you probably do the calculation wrong. So this one is just the fractional abundance. Remember, like we define this x equal to the fractional abundance of copper 63. So therefore, in this case, this is of copper 63, but it's only the fractional abundance. So if you want to know the percent, because the problem asks us to report in percent. So therefore, in this case, copper 63, the percent of this would be 69.15%, right? Because you are going to multiply 100 to this x, right, to this fractional abundance. Therefore, copper 65, right, 1 minus x, right, is going to come out to be 0.3085, but you want it to be percent, so you multiply that by 100, so it's going to come out to be 30.85%. Or you can just use 100 minus this percent of copper 63, you're gonna get copper 65. Okay, so either way, whatever you do, you need to make sure that these two add up need to equal to 100. Right? So these two, after you replace x here, these two add up, right? The fractional abundance need to equal to 1. Okay, so that's how you check your answer. And if you think about this, copper 63 here, contain more, right? The percent abundance of copper 63 is more than copper 65 in nature. So we would expect that the average atomic mass of copper would be close to the isotope mass of copper 63. Okay, so let's see if that's true. Okay, so this average mass right here come out to be closer to the mass of copper 63 than copper 65. Okay, so that makes sense, right? Because it contribute more in nature than copper 65. All right, for you to be able to do this on exam, okay, so you need to obtain the skill, right? So you need to actually do practice here. So I would like you to pause the video now and then complete this DIY problem. After you finish, then go to Moodle to check your work against the answer key that I post in Moodle. If you have any question at all, or if your work is not matching with what I have, please do not hesitate to reach out to me, okay? So far what we look at is we are looking at only just one atoms, right? But atom is extremely small. And in reality, you don't measure out just one atom, right? When you are measuring out sample of some element, it's going to contain more than one atoms. So in this section right here, we are going to learn about counting unit. Okay, so that describe things bigger than one atom. Okay, so I'm going to start with something simple first, okay, so which is 12 objects, right? So when I talk about 12 objects, everyone knows that this is equal to a dozen, right? So when I said a dozen eggs, everyone knows it's equal to 12 eggs, right? Now, what about if you have this many objects then, right? So 6.022 times 1023 objects, that's a lot, right? So that's a lot of objects, right? So what would that, how can we describe that? So this is going to be represented as 1 mole. So that means whenever we talk about mole, right, it's equal to this object. So that means it doesn't matter what it is. So if I say that 1 mole of eggs, that is going to equal to 6.022 times 1023 eggs, right? So that means this object here can be anything. You can use it as with eggs, but in the context of chemistry, we are going to use most with number of atoms, right? Number of molecules, or number of compounds and things like that, right? So you are going to see this often in terms of atoms and molecules. Okay. Okay, so this conversion right here, you have to know. Okay, so you have to know by heart. This is the heart of chemistry. You're going to use this throughout the whole sequence of chemistry. Even when you take upper class, such as organic chemistry, you are going to also have to come back to this conversion as well between mole and number of objects. Okay. So the number that you see, 6.022 times 1023, is what we refer as Avogadro's number. Okay, and the object, as I mentioned, can be anything. Okay, so it can be atoms, can be molecules, can be number of people, right? So if I said 1 more people, that is going to represent how many people? 6.022 times 1023, right? So that's a lot of people. Okay, so if you have this many objects, 6.022 times 1023 object, or 1 mole, the mass of this 1 mole is what we call molar mass. Okay, so molar mass is the mass of 1 mole. So the mass of 1 mole is going to come out to be in the unit of grams per mole, because you are measuring out a lot of object now. So therefore, it's not just one atom anymore. If you measure out the mass of one atom, that is so small that we are going to use a small unit such as AMU, right? But in this case, you are describing more than one atom. You describe a lot of atoms or a lot of molecules, right? So therefore, in this case, the unit that we can use for mass is going to be in grams. Okay, so now because it's reported in grams, so therefore it's going to be more convenient when you do it in the lab, right? So when you measure out things in the lab, we have to measure out in grams anyway, so it's going to be more convenient anyways. Okay. Now the next thing is we are going to compare between the difference between molar mass versus atomic mass. Okay, so atomic mass, if you're looking at atomic mass of iron, so this is going to be the average atomic mass of all isotopes available in nature for iron. The same thing that we learned previously, right? So you can look this up from the periodic table. Okay, so that is going to be, if you see iron, it would be 55.845 AMU, right? So it would be the number that contains decimal point. Now it's turned out that the molar mass of iron is, if you have 6.022 times 1023 atoms of iron, or 1 mole of iron, right? The mass of iron of 1 mole of iron come out to be 55.845 as well, but it's going to be in different units. Okay, so the number come out to be the same, but they are going to have different units. Okay, so the unit of molar mass would be reported as grams per mole, which means that if you have 1 mole right? So if you have 1 mole of iron, which is 6.022 times 10 to the 23 atoms of iron, this is how much it's going to weigh. It's going to weigh it's going to weigh 55.845 grams. But if you have just 1 atoms of iron, it's going to weigh this 55.845 AMU, atomic mass unit. This AMU again is very small, right, compared to grams, because we define that if you recall from the previous slide, right, so we is equal to 1 AMU. So that means in this case, if you compare between these two values right here, right, so in terms of grams and in terms of AMU, you see that AMU is a lot lighter than in grams, which makes sense, right? Because mass of just 1 atom is have to be lighter than mass of 6.022 times 10 to the 23 atoms anyways, right? So that's why the AMU and the grams are not the same. Okay, so they are not the same. The molar mass and Avogadro's number can help you to do conversion, that changing from mass to mole to number of object. Okay, so how can we do that? Okay, so let's take a look at this. If you know the grams of a substance, you can change to mole by using the mole, because the unit of molar mass is in grams per mole. Okay, so in this case, the number that go with grams is going to be the number that come from the periodic table, and it's always going to be per 1 mole. For example, iron, right? So the number that go with grams would be 55.845 grams in 1 mole of iron. Okay, so for example, if you have, let's say, like 5 grams of iron, how can you convert that to mole? Well, you are going to use this conversion right here, right? That changed from grams of iron to mole. Okay, so set up the same way that we learned in chapter 1.5. Now, if you want to convert from mole to the number of objects, you can use that as well, but not the molar mass. You are going to use the Avogadro's number, because Avogadro's number tells us about the number of objects. Okay, so this is going to be always be 6.022 with the object, right, divided by 1 mole. This is going to be always 1 mole on the bottom. So again, the number of objects here can be anything, right? It can be atoms, it can be ions, it can be molecules or particles. So this object right here, right, you can replace as any of these, right? Depend on what the problem given to you. Note that this broad map here has 2-way, right? You can go from grams to mole to object, and you can also go from object to mole and mole to grams as well by using the same conversion, but you just need to flip it, right? So this can be flipped depend on what unit you want to cancel. So for example, if you want to cancel grams, right, gram have to be on the bottom and mole have to be on top. You need to flip both number and the unit. Same thing here. If you want to cancel object, the number of object have to be on the bottom and the number of mole have to be on top, right? And if you flip the unit, right, you also need to flip the number as well. Okay, so keep that in mind. Now let's take a look at if you have 1 mole of lead versus 1 mole of magnesium. Do you think that both of them would have the same mass? Yes or no? The answer is, okay, so if you're not sure, let's go back to this, right? So if you're looking at lead versus magnesium, right? So lead Pb is right here. Magnesium Mg is right here. Number that will tell us about the average atomic mass and molar mass, the answer is going to be this number right here, right? So this one, if it's reported in AMU, right, it's going to be atomic mass. If it's reported in grams per mole, right, this is going to be molar mass. Okay, so note that you know how to differentiate that. Same thing for lead, right? So this number right here, if this number report with the AMU is represent a mass of 1 atom. If it's reported in grams per mole, it represent the mass of 1 mole of lead. You probably notice that lead is going to be a lot heavier than magnesium, right? So that means if we go back to this slide right here, the mass of 1 mole of lead will not be equal to the mass of 1 mole of magnesium. What about the amount of atoms then? So would they both have the same amount? The answer is yes, because 1 mole of lead, right, is going to have the same number of atoms as 1 mole of magnesium. Because 1 mole contains 6.022 times 10 to 23 atoms of lead, right? And then for magnesium would be the same 6.022 times 10 to 23 atoms of magnesium. Right? Remember, each of lead and each of magnesium, they weigh differently, right, in MU. So therefore, the mass in gram, they are going to weigh differently as well. So that's why the mass will not be equal, but the number of the atoms will be the same. Next, we are going to apply the idea of molar mass and Avogadro's number to help us do exercise number 4. Okay, so in this case, just again, note that molar mass will help you to convert between grams and mole, right? Because the unit is in gram per mole. And Avogadro's number will help us convert the number of objects to mole, right? So I'm going to write these two up here so that way you know what we need to use. Okay, so in this case, we have nickel is given as nickel 35.5 grams of nickel. Okay, so the problem asks us to convert in mole. So therefore, if you're looking at this, right, so it's giving us grams, which is the mass. Okay, so it's asking for mole. Which one of these two, the contain mass, the unit of mass, and the unit of mole? The answer is molar mass, right? So therefore, we are going to use molar mass in this case. Okay, so I'm going to use molar mass. How do I know molar mass of nickel? Well, this is when you will need to look at the periodic table, right? So find nickel for me. So if you're looking at nickel, so this is nickel right here. So we have two numbers. The number that represent the molar mass, so it would be the number with the decimal point right here, like 58.693. Okay, so this one should be reported as AMU or grams per mole. The answer is you need to use grams per mole because you are converting from grams to mole. We are not looking at just one atom. If you're looking at just one atom, then it will be AMU. But in this case, we're not looking at just one atom. We're looking at in 6.022 times 10 to the 3 atoms, right, which is 1 mole. So therefore, we are going to report this number with grams per mole. So I'm going to go back to this problem number 1 again. So the next thing is we know that nickel, 1 mole of nickel, right? If I do 1 mole of nickel weighs 58.693 grams. If I set up this way, you probably notice that the mole is on the bottom, the grams on top. These 2 grams will not be able to cancel out, right? Because you can't cancel those two. If those two multiply, you are going to end up with grams square, and your final unit would be grams square per mole. That's not what we want. We want just mole. Therefore, mole have to be on top, right? So because mole at the end have to be present as the unit part of the numerator. So in this case, you need to flip this. Okay, so you need to flip this because it's incorrect. Okay, so this is incorrect. You have to flip it. So therefore, if I set this up correctly, it would be 35.5 grams of nickel. Okay, grams have to be on the bottom and mole have to be on top. So that way you get mole at the end. So 58. So again, when you flip the units, you also need to flip the number as well. So 58.693 is still going to be with the grams, right? So this is how much 1 mole of nickel weigh, right? It's weigh 58.693 grams. Okay, so if you do this correctly, grams will cancel out. Therefore, you are going to get the mole as the final unit. Okay, so it's going to come out to be 0.605 mole of nickel. Okay, so 3 sig fig, right? So therefore, this is going to be 3 sig fig as well. The next question is how many atoms of nickel are in this 0.605 mole of nickel then? Right, so if you're looking at this conversion, you probably notice that we want atoms, which is the number of objects, right? And we are given in mole. So mole and atoms, these two are going to be connected by Avogadro's number. So that means we are not going to use molar mass in this case, right? Because it doesn't involve with mass in grams, right? It's involved with the number of objects. So therefore, I'm going to use Avogadro's number. Okay, so I'm going to start with 0.605 that is given, mole of nickel, right? So in this case, again, I want to cancel mole and I want atoms to be the final answer. So that means the atom have to be on top, right? The number of objects, and then mole would be on the bottom. So in this case, if you use the Avogadro's number, right? So 1 mole of nickel going to contain 6.022 times 10 to 23 atoms. Remember, I replaced this object, right, to the correct type of top object, right? So in this case, described as atom. So that's why I replaced that object with atom. Okay. So cancel the unit mole. So the answer would be 3.64 times 10 to 23 atoms of nickel, right? So that would be the answer. So given 3 sig fig, so final answer would also be 3 sig fig as well. So that's good. Another way to check this answer, remember mole is a big unit, right? That it describes this many objects. So therefore, when you convert from big object to small object, right, the number that come with a small object would be a huge number, which makes sense, right? It's come out to be a lot bigger than this 0.605, right? The number with that go with the bigger unit. So far you see only 1-step calculation. So the next example will give you a more multi-step calculation. Okay, so this one giving us atoms of silver, asking us the mass in pound. Okay, so if you see this, you probably notice that it's giving us the number of objects. Okay, so atom, right? So it's giving us this, right? So the number of object. It asks us the mass. Which one of these is associated with mass? The answer is, it's the molar mass, right? But the molar mass is in grams. But this one, it asks us in pounds. So therefore, in this case, you probably have to end up converting grams to pound at the end, right? So that's kind of like going, you see the connection, right? You probably have to put all this puzzle together, right? So again, it's giving us atom, which is the object. Somehow you need to use this information in order to have to go to from the number of object to mass, right? And then convert that mass in grams because the problem asks in pound. Okay, so how do we do this? Okay, so let's start. So I'm going to start with what's given, which is 1.42 times 10 to 24 atoms. In order to go from the number of objects to grams, you probably notice that they both connect by mole. Right? So these two are connected by mole. So therefore, in this case, I'm going to start with what's given and then use the information, which is the conversion factor right here. So I know that 6.022 times 10 to 23 atoms of silver, right, equal to 1 mole of silver. So note that the reason why I have to flip this because I want to cancel atom, right? If I have this object per mole, I won't be able to cancel the number of object, right? So that means I have to flip that Avogadro's number. So now check the unit. Okay, so atom would cancel out. I already used this information, which is the Avogadro's number. The next thing we need to use is going to be the molar mass because it's connect us to mass, right? So in this case, I'm going to continue my next step, right? So in this case, going to be every 1 mole of silver is going to weigh a certain amount of grams. So what would that be? This is when you will need to find out this number from the periodic table. Okay, so I'm going to go to the periodic table. Silver is right here. If you're looking at this, 107.87. So that is going to be the mass, right, of silver that report in grams per mole. So therefore, in this case, I'm going to write that out. Okay, so it's going to be 107.87 will be grams. Okay, so this is come from the periodic table. So if you stop now, let's check what would be the unit. Mole cancel out. You are going to get grams as the unit. That is not what we want. We want pound. So therefore, you need to add one more step. Next, we will need to convert from grams to pound, but I run out of space. I'm going to start right here. So I'm going to multiply by, we want to convert from grams to pound. Okay, so grams is metric unit and pound is English unit. So therefore, I need to look up from the list of the conversion factor that we learned in the previous chapter. Okay, so it's turned out at 453.59 grams equal to 1 pound. So therefore, in this case, if I check the unit again, grams would cancel out. So therefore, at the end, I have pound on top, right, which is exactly what we want. If you do this calculation correctly, you are going to get 0.561 pound. Come out to be 3 sig fig, right, because this is contain 3 sig fig right here as the smallest number of sig fig. Let's take a look at if this answer makes sense or not. Okay, so the number that's given to us, this unit right here is a small unit, right? So atom is tiny, so you need many of them, right, in order to equal to a number with the bigger unit, right? So the number of the bigger unit, which is pound, is come out to be smaller value than this number right here. Makes sense? All right, for next example, I want you to use the molar mass, Avogadro's number, and the given information to solve for this problem right here. Pause the video now, complete it, and resume the video again when you finish. All right, now let's check your answer together. Okay, so this is what I have here. So pretty much you are going to convert from pounds to grams first, right? Because you need to use the molar mass, which is in gram, and then use molar mass of silver, which can be found from the periodic table. Okay, so the number with the decimal point. Okay, and then after you convert to mole, then you are going to use Avogadro's number to convert to number of atoms. Okay, so this would be how many atoms of silver in 2 pounds. Okay, so it makes sense because the number of atoms have to come out to be a big number. So this is a larger number than these two right here. Okay, so it makes sense because atom is a smaller unit than pounds. The last example here, I would like you to pause the video and do it yourself first. Okay, so after you finish, then resume the video to check your work against mine. All right, let's check your work together. So there are 2 ways to solve for this. Okay, so either way would be fine. Okay, so they both are identical to me. Okay, so one is you can use the density that's given, right? And then figure out volume later and then find out length. Okay, so the second one is going to be using the dimensional analysis to find out length. okay, right away. Okay, so let's take a look at the first method real quick by using the density. Okay, so in this case, we know that the density is given, right? So we can find out length from the volume, right? Because volume is going to be length time width time height, right? And this is telling us that it's cube, so it's implied that all the length, width, and height have to be the same, right? And then mass, you can relate this mass from the given atoms, because we already know that when you have atoms, right, you can actually use number of objects to convert to mole, and then mole can be converted to grams by using molar mass. So you are going to use those two information. So in this case, I'm going to use given atoms, convert that to mole first by using the Avogadro's number, and then multiply by its molar mass to get into mass, right? So that way mole cancel out, right? Atoms cancel out. So you are going to get the mass of this silver cube to be 54.11 grams. Okay, so this is the mass part that you already know. The density is given, so that means you have one unknown variable. So if you want to solve for volume, you are going to divide mass by density. So this is the mass that you solve, right? Divide by the given density. So grams cancel out, right? So it would be like 1 divided by 1 over cubic centimeter. So you're going to flip that up. So therefore the volume will come out to be cubic centimeter. Remember, this is volume, is not the length. So in this case, because you want length, right? So the cube, the volume of cube is going to be length time length time length anyway, because all the length would be equal. So you are going to do cube root of this volume, right? So you are going to cube root this volume, and that is going to give you in length. Okay. Method 2, similar to method 1, but you are going to set all this up in one step, which is what we call dimensional analysis. Okay, so in this case, you are going to start with the given atom, convert that to mole, right? So use molar mass, convert mole to grams, and then use the density, right? Convert from grams to volume in centimeter cube. Okay, so in this case, you are going to get volume in cubic centimeter. Then you are going to do cube root again to get to length, right? So that would be identical answer for both methods. All right, here are more practice for you. Okay, so you are going to get this skill only when you practice. If you don't practice, you are going to struggle a lot on the exam. Okay, so make sure that you do all this DIY problem. When you finish, check your work, not just the answer, okay, because I grade based on your work. Check your work against the key. Okay, so if you have any problem or any question at all, please do not hesitate to reach out to me. Okay, so don't forget to check your work against the key on Moodle. Here is what we went over for chapter 2.2. Okay, so along with this information right here, you now should be able to complete homework chapter 2.2. Okay, so those homework assignments right there.